This video is going to focus on a mini review of NMR spectroscopy, specifically proton NMR spectroscopy. And what do we know that's important for NMR spectroscopy? Chemical shift tells us what kind of environment our proton is in. Integration is important in that we need to know the relative number of protons for each signal. And multiplicity tells us the neighbors around each protons. For example, a triplet means that a proton has two neighbors. We also want to remind ourselves of the chemical shifts of the different protons. The farther we are from the aromatic groups or polar functional groups, the further to the right of the spectrum we're going to be. And then when we get to groups like aldehydes and carboxylic acid, that's when we get our really large numbers. And where we're really focused in this section is in the aryl region, because we're going to have a lot of aromatic protons, and you're going to have at least one question on the exam that focuses on the NMR of aromatic compounds. We want to be aware of the symmetry of benzene rings in proton NMR spectra that lead to different numbers of signals. For example, for one signal, these are the arrangements of protons that will give you just one signal. And then we've got two signals has these arrangements where we've got X and Y para to each other, or X and X ortho to each other. We've got three signals with where we can divide a ring in half. Those are our three. And lastly, four signals is the least symmetry of them all, where we have an X and Y ortho to each other and an X and Y meta to each other. So this is another handy chart that you could print out and use while you're practicing NMR spectra. So let's get right to it. In our first example, we have the formula C10H14 that tells us that the degrees of unsaturation, or hydrogen deficiency index as your book calls it, is 4. So we know that we're looking for a benzene ring, and we're further supported that we're looking for a benzene ring because of this peak in the aromatic region. This has a relative integration of 2, and we notice that the ratios of 2 to 2 to 3 don't add up to 14, they add up to 7. What that means is that the real number of protons is 4 and 4 and 6. Because these are just relative ratios, they're not necessarily the total number of protons. So we know that in our aromatic ring, we want to have a substitution pattern that leaves us to one signal that's a singlet. So we need to have symmetry here, which means that our groups are going to be opposite each other, since we know that we have two different groups. And what is the identity of these groups? Well, they must be the same as each other in order for our compound to have only one signal in the aromatic region. And when we go over to look at these groups, we see a quartet with an integration of 2 and a triplet with an integration of 3, and that is what matches an ethyl group. So this compound is diethylbenzene. In our next example, we also have a hydrogen deficiency index of 4, so we're going to have a benzene ring further confirmed by these protons in the aromatic region. What stands out to me here is this singlet with an integration of 6, and this singlet is next to, it's going to be an ether group, and that's because of its chemical shift being at 3.5 ppm. So there are going to be 2 of them because we have a relative integration ratio of 6. And that's all that's going to be connected around this benzene ring. And what we need to know now is what has an integration ratio of 1 to 3. The 3 is definitely going to be overlapping peaks here. It's not just going to be 1. If we put the groups meta to each other, then we've got, we have protons here that can be one of these peaks, and then the remaining 3 protons are going to be in the peaks of 3. So meta-dimethoxybenzene is the answer to this question. In the next question with C9H10O, now we have a hydrogen deficiency index of 5. And what stands out to me right away is this peak at about 10.5 ppm. This tells us that we have an aldehyde. And that gives us our 5th degree of our hydrogen deficiency index. And that means that our other 4 degrees are coming from the aromatic ring, which has peaks in a 1:2 ratio. We also have peaks here, so we're going to have 2 methyl groups, and because their chemical shift is 2.5 ppm, that means that they're going to be connected to an aryl ring, or that benzene ring. So we've got to arrange our substituents where we have 2 methyl groups, an aldehyde, and an aldehyde around our benzene ring, so that we get a ratio of 1 to 2 protons. And the way to do that is to put the 2 methyl groups ortho to the aldehyde. That gives us our single proton here, and then our 2 protons there. Next we have C9H12O. That's got a hydrogen deficiency index of 4, and we see that we're going to have a group with oxygen, and let's start out by figuring out what that group with oxygen is. We know that it's not an alcohol because we don't see one of those broad peaks between 2 and 5 ppm, so it's going to be an ether, and it's going to be an ether that's part of this singlet at around 3.5 ppm. So we know that we've got a methyl ether as part of this compound. Our peaks at here, and here tell us that we're going to have an ethyl group, because we've got a ratio of 2 and 3 to those peaks, and they're a quartet and a singlet. That's the key hallmark of an ethyl group. So we've got to figure out how to put the methoxy and the 1 ethyl group around our benzene ring so that we've got a 2 to 2 ratio of protons. And what I'm going to tell you that the answer here is the meta-substituted compound, but from this ratio of 2 to 2 peaks, you actually don't know that. It could match the ortho-substituted compound or the para-substituted compound, although in the case of para, the peaks would look cleaner than this. So in a problem like this, you would be given credit for this right answer, of course, but also if you had answered ortho or para, then you wouldn't be discounted any points because the spectrum doesn't differentiate which isomer that you have. In our next example, we have an N2O4 group in the mix, and what that tells me is that we're likely to have 2 NO2 groups, because that's a lot of oxygen and nitrogen for such a small molecule. So I'm just going to say we have 2 NO2 groups. And then what else do we have left? And that takes care of the N2O4. Then we've got a methyl group, and its chemical shift is about 2.5 ppm. So that tells us that our methyl group is going to be attached to a benzene ring. And we have to figure out how are we going to get a ratio of 2 to 1 protons, with very nice splitting here. So we want to have an arrangement of our nitro and methyl groups like this, so that we've got this nice left to right symmetry that gives us a 2 to 1 ratio of peaks. Note that you could have put the nitro groups here, and you'd also get the same integration ratio, so we wouldn't discount you if your answer was that, but it happens to be the ortho compound that is the correct answer. In our last example, we've got a nitrogen atom in this formula C7H5N, which gives us a hydrogen deficiency index of 6, which is a lot of hydrogen deficiency for a small compound like this. So we know that we're going to have protons in an aromatic ring because we can see aromatic protons here. And what should also stand out to you is that all we have are aromatic protons. And because we have aromatic protons only, that means we can't have a proton anywhere else except for on the aromatic ring. So that means all 5 of these protons need to go on the aromatic ring. And what we're left with is a carbon and a nitrogen atom, which gives us a cyano group or nitrile. So our answer to this question is benzonitrile. And that is the end of this video. I hope it was helpful.